Hello everybody, welcome back again. In this video we are going to solve a numerical related to the soil moisture and crop relationship. Okay, and before this video we have already done five numerical. Okay, that was very important, and that all numerical were taken from the world question, and all questions are already asked in our university exam. Okay, and today we will start from the sixth numerical. Okay, so you can see here this is our sixth numerical. Okay, and this question is also asked in Pokhara University 2013. Okay, and we will solve this numerical. Okay, given over here, and I first strongly recommend you please visit our fifth numerical. Okay, that we have done in previous video. Okay, and I will keep the link of those video in description box. You can simply visit from there. Okay, so before starting the solution of this numerical, if you are new to the channel, please like the video and subscribe the channel. Okay, so let's see the solution. Okay, we have a question here. Find the delta for a crop when its duty is 864 hectare per cubic on the field. The base period of a crop is 120. Okay, so in solution first we have to write given data. So here in the question duty is given 864 hectare per cubic. Okay, so this is the duty, and duty is simply denoted by D, and the base period is also given over here, B equal to 120 days. Okay, and after giving these two data, we have to calculate the delta. Okay, and as we discussed in previous video, and we have already done the derivation of delta. Okay, and after calculating we have found delta equal to 864 B by D. Okay, and simply after putting the value of B and D, we can calculate the value of delta. Okay, and the value of B is taken 120 and D is 864, and after calculating this value we can simply get the delta for this value is 120 cm. Okay, in this way we can calculate the value of delta when duty and base period is given in the question. Okay, so this is all about this numerical. I hope you guys are understand. Okay, thank you very much. If you like the video, please do like, share and subscribe the channel. And now we will start the seventh numerical of this related to this topic. And you can see here this question is also taken from the world question. This question is already asked in PU 2012. Okay, so let's read the question first. Water is released at the rate of 20 cubic. So discharge at a canal head is given over here 20 cubic, 12 cubic at the head of canal. If the duty at field is 1250 hectare per cubic, and duty is also given, I already told you duty is simply denoted by D. Okay, and loss of water is 25%. Loss of water in transit is 25%, and find the area of field land that can be irrigated. So we have to calculate the area of land that can be irrigated. Okay, so with the help of this data we have to calculate the total area that can be irrigated with the help of given data in the question. Okay, so we have to calculate this. So let's start the solution. So you can see here 25% loss. Okay, so after the loss of 25%, the remaining percentage of water the remaining percent is 100 minus 25, then it becomes 75%. Okay, so total remaining water is 75% after the loss of water in transit. So now we have to calculate discharge at the field. Okay, so simply discharge at field becomes the total discharge is 12 in, or you can say simply 75% of the total discharge. Okay, so 75% means 0.75 and total discharge is 12. Okay, so after calculating this value we get a discharge at the field 9 cubic. Now we have to calculate duty at the field. Okay, and duty at a field is already given in the question. You can see here duty at a field is 1250 hectare per cubic. Okay, so this is given in the question, and we have to calculate the area of field in the land that can be irrigated. So we can calculate the area of area that can be irrigated equal to you can see here discharge at field is 9 cubic. Okay, but we have a total duty is given 1250. Okay, so we have to multiply this value with the discharge at a field. Okay, so discharge at a field is 9 and we have the total value is 1250. Okay, duty value is 1250. So we have to multiply. Simply you can write like this: duty into discharge at field. And before this video we have already done different numerical related to this. The area can be calculated with the help of this duty into duty and discharge. Okay, then its value become 1.125 into 10 to the power 4 hectare. Okay, in this way we can calculate the numerical. So the area irrigated becomes 1.125 into 10 to the power 4 hectare. And I have to say one thing here. After multiplying this value, we can get 1250 into 9. Then we get 11250. Okay, but you can see this is not in a hectare. Okay, this is in meter square. Okay, for the converting this value in a hectare, we have to divide by 10 to the power 4. Okay, as we know, 1 hectare equal to 10 to the power 4 meter square. Okay, because 1 hectare means simply 100 into 100 meter. Okay, then it becomes 10 to the power 4 meter square. So for the converting of this value in hectare, we have to divide with this value. Okay, or you can simply say 10 to the power 4. So after dividing 10 to the power 4, you can see here after this value becomes this, and we have to divide this value with 10 to the power 4. So after dividing this value we get 1.125, and we have to multiply it also 10 to the power 4. So area irrigated found 1.125 into 10 to the power 4 in hectare. Okay, or you can also left in the meter square as well. So in this way we can calculate the area of the field land that can be irrigated with the help of this given data. Okay, so this is all about this numerical. Thank you very much. Okay, please do like, share and subscribe the channel. Now we will start the 8th numerical of this chapter. Okay, and we have this question given over here. This question is also taken from the world question. So let's first see the question, then we will see also the solution of this numerical. And we have given question: 10 cubic of water is delivered to 32 hectare field for a 4 hour. Okay, we have given total area of 32 hectare, and the charge is 10 cubic, and the time is with time that the water is provided 4 hours, and soil probing after irrigation indicates that 0.3 meter, okay, of water has to be stored in the root, and compute the water application efficiency. Okay, in this numerical we have given this data, and we have to compute the water application efficiency. Okay, and we have already studied about the water application efficiency. I can show you here, and you can see here the all type of efficiency. For the irrigation efficiency we have already studied in theory part. Okay, so if you have not seen this theory part, then you have to see first the theory part. Okay, so in theory we have studied about the water application efficiency, and this is equal to the output by input water. Okay, and for this we have to calculate the output and input value. Okay, so let's see the solution. Volume of water applied. Okay, we have to calculate volume of water, total volume of water. Okay, so you can see here for total volume of water we have to multiply. So as we know, the volume can be calculated with the help of Q and T. Okay, whenever the discharge and time is provided, then we can simply calculate on the volume, and the volume formula volume becomes volume equal to Q and T. Okay, so we have given our discharge is 10 cubic. So first we have to write given discharge equal to 10. Okay, and time is also given, that is 4 hours. Okay, so with the help of these two values we can calculate the volume of water applied equal to 10 into 4. Okay, but you can see here 4 is in hour. Okay, so we have to convert this hour into second. For this we have to multiply 60 into 60, then it goes in meter, and after 60 it go in second. Okay, so in this way we can calculate the volume of water, and this becomes 44.4 into 10 to the power 4 meter cube. Okay, and after dividing the 10 to the power 4, as I said in the previous numerical. Okay, in this numerical, for the conversion of meter square meter cube into hectare, we have to divide by 10 to the power 4, converting into hectare, because we have already I have already told you 1 hectare equal to 10 to the power 4 meter square. Okay, that's why we have to divide this value with 10 to the power 4. When we divide 10 to the power 4, the value becomes 14.4 into 10 to the power 4 meter square. Okay, and you can write the 10 to the power 4 is hectare meter. Okay, then its value becomes 14.4 hectare meter. Okay, now you can see here the total input is 14.4 hectare meter. Okay, we have calculated, and the output equal to 32 hectare land storing water up to 0.3 meter depth. You can see here soil probing after irrigation indicates that 0.3 meter of water has been stored in a root zone. Okay, so 0.3 is stored in a root zone, so we have to multiply with this value. Okay, 0.3. so you can see here total delivered to 32 hectare field. We have total field equal to 32, so we have to multiply with depth, or you can write like this, total area into depth. Okay, then this value become 9.6 hectare meter. Okay, why this is in hectare meter? Because we have already given the area in hectare, that is 32 hectare. Okay, that's why the output value is also becomes in 9.6 hectare meter. Okay, that's why we have to convert this input value also in hectare meter. And as we know, whenever the two different value have same unit, then we can calculate the efficiency. Okay, and now we have to calculate the water application efficiency, that is NA equal to output by input, and the value of output we have already calculated, that is 9.6, and the value of input is also calculated 14.4. So after after calculating this value, we get the water application efficiency, that is eta A equal to 66.67%. Okay, so I hope you guys are understand, and in this way we can calculate the water application efficiency, that is asking the question. In this way we can solve this numerical as well. So I hope you guys are understanding well. if you have any queries that you can't understand, then you can simply comment below. I will reply. Okay. So this all numerical are related to the basic concept of this chapter. Okay, when you have basic concepts strong, then you can calculate these all value, and you can solve these all numerical. Okay, now we will see next numerical. And you can see here in next numerical we have this question. Okay, and this question is already asked in Pokhara University 2018 spring. Okay, so let's see the solution of this numerical. So we have given a question: a stream of 130 liter per second was diverted from a canal, and 100 liter per second were delivered to the field. An area of 1.6 hectare was irrigated in 8 hours. The effective depth of root zone is 1.7 meter. The runoff loss in field 420 meter cube. The depth of water penetration varied linearly from 1.7 meter at head end of the field, 1.1 meter at the tail end. Moisture capacity is given 20 cm per meter. Depth of soil, and we have to find water conveyance efficiency, water storage efficiency, and in third number water distribution efficiency. Okay, so we have already studied about these three different efficiencies. Okay, I can show you again. Okay, so first in one is water conveyance efficiency. So water conveyance efficiency equal to the ratio of amount of water applied to the land to the amount of water supplied from the reservoir. And water storage efficiency. Okay, and these all efficiency are is given here. We will see these all efficiencies during the solving this numerical. Okay, so very first we have to calculate water conveyance efficiency. Okay, and the water conveyance efficiency is simply denoted by NC. Eta, you can say eta C. And also the moisture extraction 50% of available moisture is given in the question, or you can say 50% moisture was present during the starting time. Okay, in the question sometimes by the giving these statements we have to ask this numerical, or sometimes in the question say like this: 50% of moisture was present during the starting time. Okay, so whenever these two are given, we have to understand these two are the same thing. Okay, so in very first we have to calculate water conveyance efficiency, and water conveyance efficiency denoted by eta C, as I told. So this value becomes water delivered to the field with the water supply into canal at head. Okay, and you can see in the question this value is already given. Water delivered to the field is given in the question is 100. Okay, I can show you here, and you can see here the total water supply a stream of 130 liter per second was delivered. Okay, it means this water is supplied to the field. Okay, so this value is taken 130 water supply, and water delivered to the field is 100. Okay, and after calculating this value we get 77% of efficiency of water conveyance efficiency, or you can say the value of NC eta C equal to 77%, that is water conveyance efficiency. Now we have to calculate water application efficiency. Okay, for water application efficiency we have this formula: water stored in a root zone during irrigation by water delivered to the field. Okay, so we have this basic formula, as I already discussed in theory parts. Okay, and I have already shown you. Okay, so we have to calculate water stored in root zone and water delivered to the field. Okay, so we have to calculate water supply to the field during 8 hours. Okay, so we have given discharge is 100. Okay, so we have to multiply Q into T. Okay, so discharge is given 100. Okay, and this value is already used here, you can see here. Okay, so we have to just take this value 100 into time is already given in the question, 8 hours. You can see here 1.6 hectare watt irrigated in 8 hours. So we have to multiply with time, Q into time gives water supplied. Okay, and we have to convert this time into second, so we have to multiply 60 into 60, then its value becomes 2880 meter cube. Okay, now we have to runoff loss in field is 420 meter cube. Okay, this is given in the question, you can see here. The effective depth of root zone is 1.7 meter and the runoff loss in field is 420 meter. So we have to minus this value. Okay, because the water stored in root zone is after the runoff loss. Okay, that's why we have to minus this value from the water supply, total water supplied. So the total water supplied is 2880 minus we have to minus the runoff value, that is 420. Then the water stored in the root zone becomes 2460 meter square. Okay, now we can calculate the value of water efficiency with the help of this formula. Okay, water stored in a root zone during irrigation is 2460, and by the water delivered to the field, and we have calculated water delivered is 2880. Okay, so we have to just keep these two value over here and in this formula, then we get the water application efficiency, that is eta A equal to 85.4%. Okay, and now we have to calculate the water distribution efficiency in very third number. So let's see this. Water storage efficiency is equal to the water stored in a root zone during irrigation by water needed in root zone prior to irrigation. Okay, so for this we have to calculate these two value. So first calculate water stored in root zone during irrigation. Moisture holding capacity of the soil is given in the question, 20 cm per meter depth. Okay, into 1.7 meter, that is the depth of the root zone. Okay, then its value becomes 20 into 1.7 equal to 34 cm. Or you can also write this moisture capacity into depth. Okay, and you can see in the question we have given moisture capacity okay, here given the moisture capacity is 20 cm per meter depth of the soil, and the effective depth of root zone is given 1.7. So we have to multiply these two values. So after multiplying we get 20 into 1.7. So 20 into 1.7, moisture holding capacity of a soil becomes 34 cm. Okay, now moisture already available in root zone at the time of start of irrigation equal to 50 by 100 into 34. Okay, because we have already calculated the moisture holding is 34, and the initially the water is supplied 100 and 50 is I have already shown you the 50 is the moisture that is moisture is extraction. Okay, 50%. So we have to take this value 50 by 100 into 34. After this we get the moisture already available in root zone equal to 17 cm. Now we have to calculate additional water required at a root zone. Okay, so you can see here the moisture holding capacity is 34. Okay, but moisture already available is 17. Okay, so the additional water required at a root zone equal to, we have to minus this value from moisture holding capacity of soil. So 34 minus 17, we get the value of 17 cm. Okay, and you can see here 17 by 100 into 1.6 to the power 10 to the power 4 meter cube. Okay, and with the help of this we have to calculate the total water needed in the root. Okay, so we can calculate total water needed. Okay, so total water needed for this we have to multiply this value additional water in total area. Okay, so we have 17 cm additional water required, and this can be converted into meter by dividing with 100 and into area. We have already calculated, and this is also given in the question. The total area and area of 1.6 hectare. Okay, so we have to multiply with this area 1.6, and this is in hectare, so we have to multiply 10 to the power 4 for the converting in meter square. Okay, so after calculating this value we get 2720 meter cube. Okay, total water needed. Okay, and but actual water stored in a root zone equal to 2460. That's why the water storage efficiency. Okay, and we have already discussed the water storage efficiency can be calculated. Water stored in the root zone during irrigation. Okay, and that was we have already calculated, and this value actual water stored in root zone. Okay, 2460 by the water needed in root prior to irrigation. Okay, and this value is already calculated. Total water needed is 2720. Okay, so we have to just keep this value in the formula. After calculating we get the water storage efficiency equal to 90%. Okay, now we have to calculate water distribution efficiency, that is ND. So for the ND simply we have to minus d by d, okay, from 1. So we have to calculate a small d and capital D value. For this let's calculate the value of small d and capital D. So first thing you have to know what is capital D and what is small d. So you can see here the capital D is mean depth of water stored in the root zone, and small d is average absolute value of derivation from the mean. Okay, the value of small d can be calculated with calculating mean value. Okay, and the small capital D is also calculated with the help of mean depth of water stored in a root zone. Okay, so we have 1.7 plus 1.1 by 2, and 1.7 is already given in the question. So see in the question, you can see here the depth of water penetration vary linearly from 1.7 meter at head end of the field and 1.1 meter at the tail end. Okay, so we have to just take this value 1.7 plus 1.8 by 1.1 by 2, then its value becomes 1.4 meter. Okay, now the derivation from mean at upper end equal to 1.7 minus we have to minus this value from these two value. Okay, that is 1.7 and 1.1. So after minus this value from 1.7, that is upper end, its value becomes 0.7. Now we have to take absolute value, not a negative value, and derivation from the mean at lower end, we have to take a lower value, that is 1.1, and we have to minus from this value this capital D, and this value becomes 0.3. Okay, now we have to calculate the average absolute value of the derivation from mean value. Okay, with the help of these two values we can calculate mean value. So we have to take 0.3 plus 0.3 by 2, then the mean value becomes 0.3. Okay, now we have to calculate the water distribution efficiency, that is eta D. So eta D equal to 1 minus small d by capital D, and the value of small d is we have already calculated, that is 0.3, and the value of capital D also we have calculated. You can see here capital D equal to 1.4. So we have to just keep this value in this formula. After calculating this value, we get the water distribution efficiency, that is value of eta D equal to 78.6%. Okay, so in this way we can solve this numerical 2. Now let's see next numerical. So now let's see the next numerical, and we have, this is the 10th numerical related to this chapter. Okay, before this video we have already done ninth numerical, okay, related to our soil moisture and crop relation topic, okay. And this is our 10th numerical, and this numerical is very important because this numerical is already asked in Pokhara University, okay. You can see here in 2019 spring and 2014 fall, and so many times, okay. So let's see the solution of this numerical 2. So if you have not subscribed our channel, please do subscribe the channel and like the video and press the bell icon, so you will get regular update whenever I upload important questions. You can get, okay, notification. That's why you have to subscribe the channel and like the video. So let's see the question is given over here. In 10th number, after how many days will you supply water to soil in order to ensure sufficient irrigation of a given crop, okay. And the field capacity of soil is given 28%, permanent wilting point, that is the PWP, is given 13%, dry density of soil, that is gamma D, is given 1.3 gram per cc, effective depth of root zone equal to 70 cm, and daily consumptive use of water for a given crop is 12 mm, okay. So these are the given question, okay, and these data are given in the question. And now we have to calculate the days, that is how many days will you supply water for these all given data, okay. The data given in the question, we have to calculate the number of days, okay. So how can we calculate? So in solution, available moisture, okay, the total available moisture equal to field capacity minus permanent wilting point, okay. So you can see here the field capacity is given 28%, okay, and we have to minus the permanent wilting point from the field capacity for determining the available moisture, okay, because the field capacity of soil is 28%, but the permanent wilting point is 13%, okay. That's why for the available moisture equal to 28 minus 13%, then the available moisture equal to 15%, okay. Now the value of RAM equal to 80% of AMC, okay, and this is the AMC. You can see available moisture content equal to AMC, okay. AMC means simply available moisture content, okay. AMC equal to 15%. So the RAM equal to 80% of AMC equal to 0.8 into 50, okay. This value, so its value becomes 12%, okay. And OMC equal to 28 minus this 12, okay. And the 28 is the field capacity. We have to minus this RAM, okay, from the field capacity, okay. Then the field capacity is given in the question is 28 minus we have calculated the RAM, okay, 12%. So we have to minus this 12% from the field capacity, that is 28% given in the question. So after minus this value, we get the value of OMC equal to 16%, okay. It means that the moisture will be between 60% and 28%, okay. Now the depth of water stored in a root zone. We have already studied about this formula in theory part, and that the depth of water stored in a root zone can be calculated with the help of this formula: gamma D into D by gamma of water into field moisture content minus optimal moisture content, okay. And we have already given this all data in the question, that is gamma of D is given in the question. You can see here dry density of soil equal to gamma of D. You can write like this also, 1.3, okay. And D is also given in the question. Effective depth of root zone equal to 70, okay, 70 in cm. So we have to convert this value in meter. So we get 70 by 100 equal to 0.7 meter. So we have to use this value 0.7, and field moisture capacity is 0.28, that is 28% given in the question. So we have to take in decimal, okay, for this formula, minus optimum moisture content. We have already calculated optimum moisture content, that is 16% by the this formula, okay, and this value calculated value is 0.16, that is 60%. So we have to take in this formula in decimal. That's why this value is taken in decimal, 0.28 minus 0.16. After calculating this value, we get depth of water stored in root zone equal to 0.1092 meter, okay, because this all value in meter, okay, and after calculating this we get this value equal to 10.92 cm, okay. So we have calculated the depth of water stored in the root zone equal to 10.92 cm, okay. So now we have to calculate the irrigation interval, okay. So for the irrigation interval we use we have to divide. So simply we can calculate irrigation interval equal to depth of water stored in root zone. We have to divide this value by daily consumption of water in given crop. So with the help of this formula we can calculate the irrigation interval, and the depth of water stored in root zone we have already calculated, that is this value is 10.92 in cm, okay. So 10.92 in cm, and the daily consumption of water in a given crop is given in the question. Daily consumption of use of water given for a crop is 12 mm, okay. But you can see here this is in cm, but this is in mm. So we have to also convert this value either in cm, or we have to convert this value either in mm, okay. So this value is cm, so let's convert this value in cm. So 12 mm means 12 by 10 equal to 1.2 cm. So we have to keep this value, and these two value have the same units, cm and cm. That's why the irrigation interval becomes 9.1 days, or you can say the water should be applied in every 9 days of interval, okay. So in this way we can calculate the number of days that we have to supply water to the soil, okay, in order to ensure sufficient irrigation of a given crop and given for this data, okay. In this way we can calculate simply. In this way we can calculate the irrigation interval, or you can say the number of days that are required for the irrigation, okay. So in this way we can solve this type of numerical. So hope you guys are understand. If you have any queries or any concern, then you can comment below, okay. Thank you very much, and let's see also next numerical. Let's see this numerical, okay. This is the 11th numerical, okay. I will write here this is 11th numerical related to this topic, and this question is also asking Pokhara University 2016 spring, okay. So first see the question. A water course is designed to irrigate an area 840 hectare of rice. The transplantation of rice takes 15 days, and during this period the total depth of water required 40 cm, okay. So base period is given 15, and command area is 840, okay. And find the daily uh, find the duty of irrigation water on the field if there is an effective rainfall of 10 cm. Okay, effective rainfall is given 10 cm and total depth of water is given 40 cm. Okay, also find the duty and discharge at the head of water course. 25% water course loss. This loss is also given over here. Okay, so given area is this, base period, water depth and effective rainfall. So we have to calculate depth of water irrigation, that is delta equal to 40 minus 10. Okay, so 40 is total depth of water. Okay, but 10 is a effective rainfall. Okay, so we have to minus the effective rainfall from the total depth of water. So this value becomes 30 cm and 0.3 in meter. So we know duty of water on a field is calculated with the help of this formula. Okay, because we have already used this formula. Okay, that is delta equal to 8.64 beta by duty. Okay, and with the help of this formula we can calculate simply the value of duty. Okay, duty means simply you can denote it by d, or we use these formulas generally 8.64 b by d. So with the help of this formula we can calculate the value of this duty. Okay, so the duty becomes 8.64 b by delta, and the value of b is also given in the question 15, and delta is 0.3. so its value become, after calculating, 432 hectare per cubic. Okay, here the conveyance loss is 25% is given in the question. Hence a discharge of 1 cubic at the head of water course becomes 0.75% cubic at the field. It is already described in the previous numerical. Whenever the loss is 25%, then the remaining equal to 100 minus 25 equal to 75%. It means 0.75. Okay, of cubic field. So we can calculate duty of head of a water course, that is capital D equal to we have to multiply this duty of water with the remaining water percentage. Okay, so 432 we have duty of water, you can write like this. This value 432 with 75% remaining. Okay, or 75% means simply you can take 0.75. so after calculating we get the duty of a value is 324 hectare per cubic. Okay, now discharge required in a water course equal to we can calculate the discharge required in a water course. Okay, and it can be calculated, or you can calculate discharge equal to, now with the help of this formula, total area by duty. So we have total area is 840. Okay, this is given in the question, and we have calculated total area equal to, okay, given in the question 840, and the duty is, we have already calculated 324 hectare in cubic. So after calculating this value we get the discharge equal to 2.59 cubic. Okay, so you can see here in the question is, in question we have to ask we have asked to determine the duty and discharge. Okay, in this way we already calculated duty equal to 324 and the discharge is 2.59 cubic. Okay, so in this way we can complete this numerical 2. So I hope you guys are understanding. Okay, so we have completed this numerical. If you have any queries, if you have any problem related to this numerical or this topic, you can comment below. Now let's see next numerical. So let's see the 12th numerical. Okay, this is our 12th numerical related to this topic. Okay, so this question is also taken from the world question, and this is asked in Pokhara University 2017 fall. Okay, so let's see the question first. The cultivable commanded area for a distributary 15,000 hectare. The total area is given 15,000 hectares. The intensity of irrigation for Rabi is 40% and for Kharif is 15%. If the total water requirement of two crops are 37.5 cm and 120 cm, okay, and total water requirement is also given, and their period growth age are 160 days and 140 days respectively, and we have to determine the outlet discharge from average demand consideration and peak demand discharge, assuming core period are 4 weeks and 2 weeks respectively. Okay, so this is the question given over here, and we have to calculate the discharge. Okay, so I have already told this question is taken from the world question, Pokhara University 2017 fall. Okay, so how can we calculate the discharge? So now let's see the solution of this numerical, and please do like, share and subscribe the channel. We have given the cultivar command area is 15,000 hectare. Area under irrigation in Rabi season is 40%, means 0.4 into this total area 15,000, then it becomes 60,000 hectare, and for Kharif 15%. So we have to take 15% means 0.5% of this total area. It's become 2250 hectare. Okay, in very first number we have to calculate for a Rabi. Base period is 160 given in the question. Delta is depth is 37 cm, and we can calculate duty equal to 864 B by delta. Okay, we have already discussed this formula, and 864 into B is base period is 160 by delta equal to 37.5. Then its value become 3686.4 hectare per cubic. Okay, similarly for the Kharif, base period is 140 day, depth delta equal to 120, and duty can be calculated as this formula, 864 into B by 120. For the Kharif, B is given 140 and the delta is 120. This value is given in the question, so its value becomes 1008 hectare per cubic. Okay, so you can see here for the Kharif is given 160 and 140. Okay, so this value is taken. Okay, now we have to calculate the outlet discharge for Rabi, and we have already discussed about this formula. Okay, for the discharge we use this formula, Q equal to area by duty. Okay, so we have already calculated the area for the Rabi is we have calculated 6,000 hectare. Okay, so 6,000 hectare we have to keep here by duty for the Rabi we have calculated 3686.4. so we have to just keep this value in this formula. Then we get outlet equal to 1.62 meter cube per second. So we have calculated this discharge, and outlet discharge for Kharif we have to also calculate for the Kharif. Similarly, area by discharge for the Kharif we have to take the area of Kharif and discharge also for the this. Okay, so we have already calculated area equal to 2250 for Kharif, and the duty is you can see here 1008. Okay, so after calculating this we get 2.23 meter cube per second, the discharge of outlet in Kharif. Okay, now the required discharge equal to, we have to take the greater value. Okay, so the required discharge equal to 2.23. okay, this is in cubic, or you can say 2.23 in meter cube per second. Now we have to calculate for the Rabi. Okay, the core period you can see in the question, peak demand discharge assuming core period as are 4 week and 2 weeks respectively. We have given in the core period B equal to 4 weeks, that is 28 days. We have to convert this value in day, and core periods, that is delta equal to 13.5 cm. Okay, these two value is given in the question. And duty, we can calculate the duty equal to 8.6 B by delta. Okay, this is core depth, or you can say you can also write like this, and this value B is 28 by delta is 13.5. okay, so after calculating this value becomes 1792 hectare per cm. Similarly, we can calculate for the Kharif B equal to 2 weeks means 14 days and delta equal to 90 cm. So we have to just keep in this formula. So B is 14 and delta equal to 90. After calculating, we get for the Kharif is 636.6 hectare per cubic. Okay, so discharge at N Rabi equal to A by D. So we have calculated area equal to 6000. Okay, and D equal to 1792. So this D is used here, and area we have calculated 6000 hectare. Okay, so we have to just keep this value. We get 3.34 meter cube per second. And similarly, discharge for the Kharif equal to area by D, and area for the Kharif is we have already calculated, that is 2250 by D. And D is for Kharif we have calculated 636.6. So after keeping this value, we get discharge for Kharif equal to 3.53 meter cube per second. Okay, and now design discharge for the peak demand. We have to calculate for the peak demand equal to, we have to take this greater value, that is 3.53 into peak demand equal to, we can calculate we have to multiply with the peak value 1.2, or you can take 1.5 as well. So in this numerical we take 1.2 peak value. So design discharge is 3.53 into peak value 1.2, then this is the peak factor. Okay, after calculating this we get 42.23 qmax. Okay, so in this way we can calculate all the value that is asked in numerical to calculate. Okay, so in this way we can calculate this, solve this numerical too. So I hope you guys are understand. Okay, so if you like the video, please subscribe the channel and share the video. Now we will solve the 13th numerical. Okay, this is our 13th numerical related to this chapter. Okay, and we will also do 2 more numerical. Okay, we have to do total 15 numerical related to this channel, this topic. Okay, so let's see the 13th numerical of this topic. A certain crop is grown in an area of 3000 hectare, fed by a canal. Field capacity of soil is 26%, optimum moisture 12%, permanent wilting point 10%, effective depth root zone 30 cm, apparent relative density is given 1.4, and an irrigation is supplied when the moisture content of soil falls to 15% at an interval of 10 days. Overall efficiency is given 42%. Okay, and we have to find daily consumption use and water discharge in meter cube per second. Okay, and this question is taken from world question Pokhara University 2018 fall. Okay, so we have to calculate daily consumption use and water discharge in meter cube per second. So how can we calculate this numerical? Okay, so let's see the solution. So we have first given depth of water used by the plant for the growth, which is supplemented by irrigation after even 10 days. Okay, so you can see here we have apparent relative density is 1.4 into this formula we have already used in previous video. I will keep here. This formula we have already used, gamma d into d by gamma of water into field moisture content minus optimum moisture content. So we have to use this formula. Okay, so gamma of d is generally take 1.4, and this is also given in the question, relative density 1.4, and d is given in effective root zone equal to 80 cm. 80 cm means 0.8 meter by gamma of water is 1, and field moisture content is given in the question is 26%. Full field capacity of soil is given 26%, so we have to take 0.26 minus optimum moisture content equal to 12%, already given in the question. So we just keep this value in this formula. After using this formula we get this value equal to 0.1568 or 15.68 cm. Okay, So depth of water stored in root zone we have already calculated, that is 15.68 cm. So daily consumption is, we have to divide this value with the total time interval is given here 10 days. So we have to divide this value with given time. So this depth by time equal to 15.68 by 10. 10 is given in the question, you can see here, at an interval of 10 days. So after keeping this value, we get 1.58 cm equal to 15.68 in mm. Okay, now we have to calculate the total water required in 10 days. Okay, so for this we have to just multiply A into day, and the area is given in 3000. Okay, you can see here total area is given 3000 hectare in the question. Okay, and D is, we have already calculated, that is 15.68. This is in mm, but we have to calculate this value in meter. Okay, because this is in hectare, so this is also in a hectare. So for the converting of hectare, we have to multiply 10 to the power 4, then it's become in meter square, and we have the depth is 15.68 in cm. So we have to divide by 100, then its value becomes in meter. So these two value have the same units, then we can calculate very easily. Then total water required in 10 days becomes 4704000 meter cube. Okay, now we have to calculate the discharge in a canal. Okay, for the discharge in a canal, we have to divide this value. Okay, this value by the time, or you can say total water, or you can write like this: discharge equal to V by T simply. Okay, we have to use this formula: discharge equal to V by T, and discharge of in canal equal to total water calculated, that is volume of water equal to 4704000 by time is given in the question is 10 day. Okay, so we have to convert in second. So 10 day means simply 10 into 24. This goes in hour, and after multiplying with 3600 we get in second. So this value becomes 5.45 cubic. Okay, in this way we can calculate discharge in a canal is 5.45 meter cubic, or you can write like this 5.45 meter cube per second. Okay, in this way we can solve this numerical. Hope you guys are understand. So for this we have you have to just use you have to remember this formula. Okay, gamma D into D by gamma of water into field moisture content minus optimum moisture content. Okay, in this way, and daily consumption is equal to D by T. We have to use this formula, Q equal to V by T. After knowing this formula, you can easily solve this numerical. Okay, so I hope guys are understand. Thank you very much. Now let's see two numerical more. Okay, so this is 13th numerical. Now let's see the 14th numerical. Okay, so this is our 14th numerical related to this topic. So let's see the question. Potato is to be grown in a field capacity 25% is given in the question, and PWP is 12%, and find soil moisture storage capacity in 75 cm depth soil. If gamma of D is 1.5 gram per cc, soil moisture fall 15%, field application efficiency 75%. What is the amount of water needed for canal outlet if loss is given 15% outlet? Calculate the time of irrigation to be applied for potato field of 4 hectare. Given area is given 4 hectare. If the available discharge of a canal outlet is 2 meter cube second. So this all data is given in the question. Okay. So now we have to solve this numerical, and this numerical is taken from Pokhara University 2017. So let's see the solution. Now let's see the solution. So please do like, share and subscribe the channel. Okay, and comment down below. So in very first step we have to calculate the maximum storage capacity. Okay, and we have already discussed about this formula. For the maximum storage capacity, we use this formula, gamma D into D by gamma of water into field moisture content minus optimum moisture content. Okay, and gamma of D is already given in the question, that is 1.5. Okay, you can see here gamma of D is given in the question, 1.5 into depth. Depth is also given in the question, that is 0.75. This is 75 cm in depth. Okay, so this is in cm. We have to convert this value in meter. So 75 by 100, we get 0.75. By gamma of water, we always take 1. Okay, and field moisture content, this is also given in the question. You can see here the field application of is field application efficiency is 75%. You can see in the question, field moisture content is 25%, means 0.25 minus optimum moisture content. Optimum moisture content is given in the question, that is PWP is 12%, means 0.12. Okay, so this all value is given in the question. After calculating this value, we get moisture maximum storage capacity equal to 0.14625 meter. Okay, or in cm 14.625 in cm. Since moisture is allowed to vary between 25 and 15%. Okay, you can see here 15% and 25%. Then deficiency created in fall. Okay, and this deficiency equal to 1.5 into 0.75 is this formula. Okay, into 0.25 minus 0.15. We have to use this percentage. Okay, 50%, that is soil moisture falls in 50%, so we have to use this value. Okay, so 0.15. Then deficiency created in fall equal to 11.25 cm. Okay, now we have to calculate the quantity of water required to supply to the field. Okay, for this we simply use this formula, NIR by eta, or you can say NA. Okay, so FIR equal to the value of NIR. We have already calculated the 11.25 by eta A. NA equal to 0.75. This is already given in the question. You can see application efficiency, that is 75. So this value is given 75%. Okay, so we have to just 0.75. Then we get the value of FIR equal to 15 cm. Okay, now after knowing this value, we can calculate simply a quantity of water needed at a canal outlet equal to FIR by NC. Okay, and the value of FIR we have already calculated, that is 15 by the NC. The value of NC is also given in the question. You can see so this value becomes 0.85, and if the value is not given, then we have to assume. Okay, then its value becomes quantity of water needed at a canal outlet equal to 17.64 cm. Now we have to calculate volume of water required to irrigate 4 hectare. Okay, so for 4 hectare we have to multiply the value of FIR. Okay, or you can like that, FIR into area. Okay, so the value of FIR we have calculated is 15 cm into 4 hectare. 4 hectare means 4. Okay, but we have to convert these two different value in same unit. Okay, so 15 cm. For calculating cm into meter, we have to just divide by 100, and for hectare we have to just multiply by 10 to the power 4. So after calculating, we get the volume of water required to irrigate 4 hectare equal to 6000 meter cube. Okay, and the time during which 6000 meter cube of water supplied at 2 meter cube per second equal to time we can calculate simply. T equal to V by so we can calculate time during which 6000 meter cube of water supplied at 2 meter cube per second. This is discharge, and this we have calculated volume. Okay, so the value of T becomes V by Q, or you can say T equal to V by Q. Okay, volume by discharge. We can calculate time. So volume is, we have already calculated 6000 by discharge equal to 2 meter cube per second. So after calculating this, we get time equal to 3000 seconds, or you can say 0.83 hour. Okay, in this way we can calculate different parameter asking the question. Okay, so I hope you guys understand. Thank you very much. See you in next video. And let's see one last numerical. This is the 15th numerical related to this chapter. Okay, and this question is taken from world question, and this question is asking Pokhara University 2019 fall. Okay, so let's read the question. The cultivable command area of a water course is 1200 hectare. Intensity of sugar cane and wheat crops 20% and 40% respectively. The duties for the crops at head of water course are 730 hectare per cubic and 1800 hectare per cubic respectively. So this is given in the question. Now we have to find discharge required at the head of water course and determine the design discharge at the outlet. Okay, so this is the question, and this is already asked in Pokhara University 2019 fall. Okay, now we have to solve this numerical. So how can we solve? So let's see the solution. First we have to write the given data. Intensity for sugar cane is 20% given in the question, and for the wheat is 40%. Okay, the duties of sugar cane and water is also given in the question, that is 730 and 1800 hectare per cubic. Okay, so this is in the question, and total cultivated area is also given 1200 hectare. Okay, so we can calculate the area to be irrigated under sugar cane equal to total area into intensity. Okay, so we have a total area is 1200 into intensity is 20%, so 0.2, its area becomes 240 hectare, and similarly for the wheat equal to 40% of total area. So 40% means 0.4 into 1200, we get 480 hectare. Okay, and we can check this value. After adding this value and this value becomes equal to with the total area, that is 1200 hectare. Okay, so this value is okay. Now we have duty for a sugar cane is given in the question 730, and duty for a wheat is 1800. So you can calculate discharge with the help of area by duty. We have already done so many numericals related to this type of. Okay, so you can easily understand. So I can do directly discharge equal to area by duty. So area is already calculated 240 by duty is 730. Okay, this is for the sugar cane. Similarly, we have to calculate for the discharge required for the wheat, and wheat equal to area by duty, and discharge required for the sugar cane. Whenever we calculate discharge for the sugar cane, we have to take the value of area for sugar cane and duty for sugar cane. Okay, so the area of sugar cane we have calculated is 240 by duty of sugar cane equal to 730. So 240 by 730, its value becomes 0.33 cubic, or you can say 0.33 meter cube per second. Okay, and now we have to calculate discharge for a wheat equal to area by duty. For the wheat, we have to take the area for wheat and duty for wheat. Okay, so for the wheat we have to take the area of wheat is, we have already calculated, that is area of wheat equal to 480. So we have to take 480 by duty of wheat is 1800 hectare per cubic. So after calculating this value, we get discharge for the wheat is 0.27 cubic or 0.27 meter cube per second. Okay, in this way we have calculated discharge as and area. Okay, so now we have to just calculate in very first number. You can see in the question, discharge required at the head of water course. Okay, so as sugar cane is perennial crop and wheat requires water for only in Rabi season. Okay, but sugar cane requires in both. Okay, that's why we have to add this value. Water required of a crop at a head of the water course equal to 0.33 plus 0.27. We have to add both these two value, that is discharge of sugar cane and discharge of wheat. Okay, so discharge required at a head of water course equal to 0.6 cubic. And in second number, determine the design discharge at the outlet. So we have to calculate design discharge for the outlet. So take the time factor equal 0.8, since the channel runs fewer days than the crop days, and we already know the channel runs fewer days than the crop days. That's why design discharge of outlet equal to 0.6 by 0.8. Okay, so 0.6 is this discharge. Okay, discharge required at the head of water, or you can like that discharge at head of water, at head by a time factor. Okay, so discharge of water head we have calculated 0.6 cubic by time factor. You can take time factor equal to 0.8. Okay, so after calculating this value, we get design discharge at outlet equal to 0.75 meter cube per second. Okay, in this way we can calculate the different value according to the question. Okay, and we can easily solve the numerical. I hope you guys understand. Thank you very much. See you in next video. Okay, so this is all about this chapter. Okay, and I hope after solving this all type of numerical, you can solve, and you are able to solve any numerical, any type of numerical related to this topic. Okay, so thank you very much, and thank you very much for your patience. Okay, thank you very much for seeing this all numerical. Thank you. See you in next video. Have a good day.